So we are resuming our section on trigonometric integrals. And what I did a little bit differently is I've already written out my work and I'm just going to talk through it. Some of these problems are extremely elaborate and it's very easy to make a minor mistake. So rather than me having the video run while I look for a mistake, I've checked everything in advance and I'm just going to talk through it. So here is another example. We want to do this integral of square root of x squared minus 25 over x. So we're just noticing the part that is perfect square minus perfect square is of the form u squared minus 25. And that's a situation where we want to use secant. So secant squared minus 1 is tangent squared. So when we have variable expression minus constant, secant's a good choice. So first thing I'm going to do is I'm just going to clearly write out, here is the trig substitution I'm making, and I'm taking a derivative and I'm getting an expression for dx. So I'm just going to substitute everything. When I substitute x squared minus 25, that's 25 secant squared minus 25, all under a radical. X in the denominator is now 5 secant theta, and dx is now 5 secant theta tangent theta d theta. So right off the bat, we notice that the 5 secant theta here cancels with that 5 secant theta. And then using our identity, secant squared minus 1 is tangent squared. So we basically have 25 copies of that here. That's under the radical. So this part becomes 5 tangent theta. And this is still tangent theta. You may always assume we're dealing with positive values in the first quadrant when you have to worry about evaluating square roots and things like that. So we have 5 tangent squared theta, and maybe you just look this one up. I would like you to remember the trick that tangent squared theta is secant squared theta minus 1. So here is our antiderivative in terms of theta. So the whole point here is by switching it in terms of theta and trigonometric expressions, we're much more likely to get an integral we know. This was not ridiculously hard. We make the substitutions, and after cancellation, it's actually a pretty nice function. Now we need to substitute back, and this is where things get a little tricky because it's not directly plugging in. We need to figure out some relationships. So I'm going to need to know what is tangent theta in terms of my original variable x, and what is theta in terms of my original variable x. So I'm just doing some work over here. I assigned x as 5 secant theta. If you're watching this because you missed class, I'm doing this much faster because it's already written down, so please hit pause as you need to. This means that secant theta is x over 5, and cosine theta is 5 over x. Ideally, we want to get things back to sine, cosine, or tangent. So if cosine theta is 5 over x, then theta is inverse cosine of 5 over x. Again, just assume first quadrant values so that everything is intuitive. To find any other trig function, I can take this equation, cosine theta equals 5 over x, and draw a right triangle to illustrate that relationship. So that's what I've done here. I've drawn my right triangle where adjacent over hypotenuse is just 5 over x. By Pythagorean theorem, here's my third side. And I need to know tangent theta, which would be opposite over adjacent, square root of x squared minus 25 over 5. And it really shouldn't shock us that along the way, we are recovering this expression, square root of x squared minus 25, that was in the problem at the beginning. It seems like some version of that will show up in our answer. Okay, so I substitute back. Tangent of theta is this expression, so I just substituted it here. Theta, we found, was inverse cosine of 5 over x, so I substitute that here. So on the left, those 5's cancel, and I have square root of x squared minus 25, and here I have minus 5 inverse cosine of 5 over x plus c. Okay, so this is a rather complicated looking antiderivative compared to the relative simplicity of our function. Now, what I did, I might not even do this in class, but here I'm checking that this works. So I'm imagining, what if we took the derivative of this thing? So there's a lot of work here. Here I'm just going to use chain rule. So 1/2 times something to the negative 1/2 times 2x. Then minus 5 times, and I'll use chain rule for derivative of inverse cosine. Inverse sine comes up a lot more often. You may have actually forgotten this, that the derivative of inverse cosine is just the opposite of the derivative of inverse sine. So that's what I'm doing here. Negative 1 over the square root of 1 minus 5 over x squared. Then by the chain rule, I need to multiply by the derivative of that inner function, which would be negative 5x to the negative 2. Let me just wall this off. It's a relevant piece of information, but it's not really part of the solution. So now let's just simplify, 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 and see what happens. So here, the 2 cancels with the 2. A negative 1/2 power means a radical in the denominator, and I have an x left in the numerator. Here, I have a triple negative, so there's a minus in front. I have 5 times 5, so there's a 25. 5 over x squared is 25 over x squared, so here's my radical. And then an x to the negative 2 is an x squared in the denominator. All right, so far so good. This one I'm keeping exactly the same. For the next one, all I'm doing is I'm creating a common denominator for the subtraction inside that radical. So I'm writing it as x squared minus 25 over x squared. Now what? So here, I'm noticing I have the square root of x squared. The square root of x squared is x, but that x would be in the denominator of the denominator. Right? There's this fraction bar and there's this fraction bar. If something is in the denominator of the denominator, we're actually multiplying by it. It winds up in the numerator. So this winds up as an x in the numerator after we take the square root. And what's left in the denominator is square root of x squared minus 25 times that x squared. So that's what I have here. So this is where I am so far. Fraction minus fraction, I'll create a common denominator. And their denominators are already similar. So I'll multiply here top and bottom by x squared to create that. Oh, actually, let me simplify that one first. Sorry, right? Because we have x here and x squared here. So we will simplify this one, and it becomes 25 over x times that radical. Anticipating that I want this as my common denominator, I looked at this fraction here and created that common denominator by multiplying top and bottom by x. So my top became x squared, and there's this extra x in the bottom. But now, both of these fractions have the same denominator, so I can combine them. My new fraction here is x squared minus 25 in the top and x times that radical in the bottom. And now I will just point out that x squared minus 25 is root x squared minus 25 squared. So we can actually cancel a copy of this radical with a copy of this radical, and we're left with the radical that's been lurking over x. And if we remind ourselves of this problem we started quite some time ago, that was what we were trying to find the antiderivative of. So figuring this out is not super straightforward. Checking it actually seems harder. Right? For so many problems, the checking is easier than the finding. For these problems, not necessarily. All right. Oh, and now I'm going to switch to another document. I changed my mind about an example as I was creating this. So last thing I want to mention before we do one more example is trigonometric substitution is something you can just layer on top of other things. And there are cases where first we're going to do a U substitution to rewrite things to look a little more like what we're used to. Then we're going to do a trigonometric expression. Right? This is especially helpful when we notice we have some kind of quadratic that doesn't quite look like x squared minus 25 or something like that. But maybe if we rewrite it in a clever way, especially if we use completing the square, we can change the form. So let me illustrate this with an example. Suppose we want to do this antiderivative. So we're integrating 1 over this radical. And what we're noticing here is that this has 3 terms. right? It's not x squared minus 13 or x squared plus 13 or 13 minus x squared. There's this extra term in the way. But any quadratic is related to a perfect square. So what I'm going to do is I'm going to say I have x squared minus 4x plus 13. Let's focus on these two terms and complete the square. So completing the square means we have to add a 4. Well, I don't have 4 at the end, I have 13 at the end. So I'm just going to take this 13 and say 4 of them go here to nice and conveniently complete the square, and the remaining 9 are here. So what I actually have is quantity x minus 2 squared, right? This is my perfect square, and perfect squares are really nice here, plus 9. So this is of the form something squared plus 9, and that's good news for us. So I'm realizing because it's something squared plus 9, it will be really helpful if I just treat that something as though it's the variable. So I'm going to make a u substitution where u is x minus 2. This is nice because du and dx are the same. Right? So it's a minimal substitution. It really just cleans it up for us. So first thing I'm going to do is the u substitution. So really the only difference is this thing now has the form u squared plus 9. dx and du are the same because u and x are so similar, right? They just differ by 2. Now we're noticing one of these patterns that's good for trig substitution. And when we have adding, tangent will be helpful. So the recommended trig substitution would be u equals 3 tangent theta. And that means du would be 3 secant squared theta d theta. So now let's do that trig substitution. So my 1 in the top stays the same. My radical is now u squared is 9 tangent squared theta plus 9. Du is this expression. Let's simplify and see what happens. This whole thing by our identity is 9 secant squared. And the square root of 9 secant squared is 3 secant. So that's where that comes from. And then I have 3 secant squared here. Well, I have some nice cancellation. The 3's cancel and a pair of secants cancel. I'm just left with secant. And this is one that you don't have to have memorized, but we addressed it. We addressed how do we find the antiderivative of secant, and this is the rule. So getting to the antiderivative in terms of theta, not so bad. Once we make the right substitution, a lot of stuff cancels, and then it should be an integral that either we know or we can quickly look up. Now the substituting back is a little more challenging. So I'm reminding myself that I said u equals 3 tangent theta. And I'm also reminding myself that u was just a temporary name for x minus 2. So let's just get back to x, right? We don't need u anymore. We're trying to get rid of theta. So tangent theta is x minus 2 over 3. I will draw a little diagram to illustrate that. Here is theta, so opposite over adjacent is x minus 2 over 3. And by Pythagorean theorem, the hypotenuse is this expression that was lurking in the original problem, so not a shock to us. In order to plug in, we're going to need to know both secant and tangent. So tangent, we've got here. And then secant, right, cosine theta is adjacent over hypotenuse. So secant theta is hypotenuse over adjacent, which is this expression here. So in terms of theta, it's the rather elegant looking, all things considered, natural log of secant theta plus tan theta. Here I have to sub back in and it's looking pretty ridiculous. But this is our antiderivative. And I have done the work to check it. Right? Some of these, it's so hard to check that we really just want to hope we didn't make any goofy mistakes. But let's give this a try. If this is our function, then the derivative would be what? We have natural log of something. So by chain rule, it's 1 over that whole something. And by chain rule, we have to multiply by the derivative of what's inside. So the derivative of this is just 1/3. And then for the other part, over 3, I'm separating out that 1/3, just getting it out of the way. And then the derivative of square root of x squared minus 4x plus 13 would be 1/2 x squared minus 4x plus 13 to the negative 1/2 times the derivative of the inside, which is 2x minus 4. So let's clean up a little bit. I am noticing this is divided by 3, this is divided by 3. So in the denominator, my common denominator would be 3. Denominator of denominator is actually the numerator, so that just winds up with a 3 up top and no fractions in the bottom. I'm also noticing that I have this 1/3 and this 1/3, so I'm pulling both of them out. And I'm already noticing I have a 3 in one place and a 1/3 in the other place, which is nice. After I pull out that 1/3, well, this was just 1/3, so 1 is what's left. And then 1/2 times 2x minus 4 is x minus 2, and a negative 1/2 power is a radical in the denominator. So let's keep simplifying. I am multiplying these things together. So these cancel, which means I really have, or let's write it this way, cross these out, and I just have a 1 up here. So I have this whole expression times the two things in those brackets, so I'll distribute. So this whole thing times 1 is what I've got here. This whole thing times x minus 2 over this, right? So this whole thing times this thing, fraction times fraction. We multiply the numerators to get x minus 2. We multiply the denominators to get this whole thing times this radical. Okay, so this is a mess, but we're noticing the denominator here and the denominator here are pretty similar. So I will create a common denominator by essentially over here multiplying top and bottom by that same radical, so that this fraction on the left is the radical that's been involved times this expression times the radical, which is the same denominator here. So I've created that common denominator. Here I get the radical. Here I have x minus 2. And now what we'll notice, right, the order is different, but hopefully we notice that this expression inside those brackets is the same as this numerator, just in a different order, right? It's x minus 2 plus that radical, or that radical plus x minus 2. So those are actually the same thing. They cancel, and we just have 1 over that radical, which is what we were trying to find the antiderivative for in the first place. So not an easy thing to check. I think I actually made a mistake in my attempt to check this, so I'm glad that I did it before I started to make the video. But this works. No one said trig substitution is fast or easy or fun, but it works. It is a technique that is available if we really need to know the antiderivative of something that has that kind of form with perfect squares added or subtracted. All right, that is it.